Hello and welcome to the final day of the 2022 SABR Analytics Conference. I'm SABR CEO Scott Bush, and we have a great schedule on tap for all of you today. We will be bringing you research presentations from David Schmerfeld and Scott Brave, as well as student presentations from Joshua Mold and Sean Sullivan. We also have a panel discussion on sports science with Will Carroll, Ryan Croton, Kristen Nicholson, and Jason Thiemanson. I'd like to thank our presenting sponsors, Major League Baseball and Rawlings, along with today's session sponsor, Blast Motion, for helping make today's programming possible. Getting us started today, our first research presenter for this session is David Schmerfeld with a presentation on defensive metrics. David, take it away.
Hey, good afternoon, everyone. Happy spring. Thanks for being here. My name is David Schmerfeld. I'm a sports analytics graduate student. Welcome to Measuring the 6%, using generalized linear mixed models to compare DRS, UZR, FRAA, and Statcast team season fielding metrics. So what do I mean by 6%? When 1984, the hidden game of baseball said that fielding accounts for 6% of the game and pitching 44%. In 2004, Moneyball said that fielding is at most 5% of the game. How do they get these numbers? Back then, we only had errors and unearned runs to measure fielding. So in 1984, when the hidden game of baseball was published, 12% of runs were unearned. So since defense is 50% of baseball, multiply that by a half, and you get the result that fielding was 8% of baseball. Now today, over the last 5 full seasons, 8% of runs were unearned. So if you do the same math, you get 4%. So does this mean that the value of fielding is only 4% of the game today? Well, that depends on measuring fielding by errors. And this is a SABR analytics seminar. So we know that errors is not the best way to measure fielding. So there's better ways to measure fielding more analytically. Here are 4 of the most common statistics. We have outs above average, which is converted to runs prevented by Baseball Savant and Statcast. In this presentation, I'm going to refer to outs above average and runs prevented interchangeably. We have defensive runs saved, or DRS, by Sports Info Solutions. We have ultimate zone rating, UZR, by Fangraphs, and we have fielding runs above average, or FRAA, by Baseball Prospectus. Now, the details for how all the calculations are made to get these statistics are very complex. And fortunately, you don't have to know those details for this research. But I do have bad news. The statistics don't always agree. How often? How often do you think that runs prevented and DRS disagreed on whether a team's fielding cost or saved the team runs over the course of a year? Answer is B, 25%, a quarter of the time. 2 of the most advanced fielding statistics disagree as to whether a team was an above average versus a below average fielding team. So here's some extreme examples for you. For the 2017 Royals, runs prevented found them to be a way above average fielding team. DRS found them to be a way below average fielding team. For the 2017 Dodgers, runs prevented found them to be way below average, and DRS, on the other hand, found them to be way above average. Okay, so those are 2 data points. How about all teams? So these are the correlations. So these are the correlations over the last 5 full seasons. So here, DRS tends to be most correlated with the others, as you see from the top row. And FRAA is the least correlated with the other statistics, as you see in the last column. The highest correlation between any two of the advanced fielding statistics was 0.526. So that's good correlation, but I'd expect it to be higher since these are all supposed to be measuring the same thing, team fielding. I have more bad news. These statistics don't just disagree on the average values, they also disagree on the variance between the best and worst fielding teams. So I just see in these box plots, the DRS box plots on the left find a wider variation in fielding talent among the teams than the other three statistics. Now, DRS was revised in 2021, but the spread stayed pretty much the same when compared to the previous years, as you see from the two box plots on the left that haven't changed much. Okay, so what fielding statistic does the best job? Well, in 2020, Baseball Prospectus did a study called Measuring Defensive Accuracy. Oops, let me go back. Measuring Defensive Accuracy in Baseball by Jonathan Judge and Sean O'Rourke. So this study compared different models to see which fielding statistic was best at predicting outs. So that means the response for the models was whether an out was made on a play or not. The conclusions that Judge and O'Rourke made are in red at the bottom of the slide. They found that FRAA was best for predicting outfield outs, while outs above average was best for predicting infield outs. So took a little bit of a different approach. And that's not because I disagreed with their analysis, but it's because I'm trying to answer a slightly different question. So the question I'm looking at is what advanced fielding statistic does the best job of showing the true value of fielding? So I'm not using outs as the response. I'm using runs allowed over the course of a season as a response. So as you see on the top of the slide here, total runs allowed is the response. The predictors are going to be runs allowed due to pitching, which I have highlighted in yellow. This is going to be home runs, strikeouts, walks, plus the runs allowed from fielding. So here I'm going to use one of several fielding statistics. I'll use either errors or one of the 4 advanced fielding statistics. So I'll make several different models, each one using a different fielding statistics and compare them. So this way we could see which of the advanced fielding statistics improves upon errors, which is the whole point. So first, here are some correlations between the fielding statistics and the pitching statistics. Generally, we don't see any correlation, but there is some moderate correlation between DRS and home runs and strikeouts, as you see on the bottom row here, with the correlations being above 0.3. At first, I didn't really expect to see any correlation between the pitching statistics and the fielding statistics, but then the more I thought about it, the more I thought that maybe teams that invest in good pitching might also be investing in good fielding. So that might be a response for the small correlation. I'm not sure. So here's the response distribution. So remember, the response is total runs allowed, and the red line shows a normal distribution. So at first, it looks pretty normally distributed. But if we take a closer look, if we look at a negative binomial response, which I have in blue, it fits the response slightly better. That's because there's some right skew here. That means that the median's less than the mean. And that happens because you can't allow less than 0 runs in a game. Now, normally that tends to even out once you get into really high numbers like we are here, around 700 and 800, but you still see some remnants of that left. So even though the negative binomial just does an incremental improvement, it still does a little bit of an improvement. So I went with it. So I'm going to choose the negative binomial and go with a generalized linear model. I'm also going to make it a mixed model. So that means I'm going to add a random effect. So here, each team is going to be a random effect. That's because there's a problem with multi-year data, and that's that each observation is not going to be independent. So for example, in my data set, there's a lot of years where the Dodgers gave up a low number of runs, and there's a lot of years where the Orioles gave up a lot of runs. So when you look at the year-to-year correlation coefficients for each team, it comes out to be 0.446. So that kind of confirms that the data points aren't independent. So to account for this, I'm making each team as a random effect. So here's a summary of my model structure, just to wrap up what I've been mentioning. The response is going to be team runs allowed. The fixed effects are going to be home runs, strikeouts, and walks, where walks are also going to include intentional walks and hit by pitches. And I'm going to include a fielding statistic. And then each team is going to be a random effect. Right, so how did the models perform? Okay, first we can look at deviance. So the model with the lowest deviance is going to do best. Okay, there's clear separation here between the DRS model and the others. So the DRS model has the best fit. UZR and runs prevented are in the second tier. And then errors and FRAA perform similarly. They're in the third tier. The none model in white here, those are pitching statistics only. So no fielding statistic is used in those models, in the none model. So when you compare the none model to the other models, these are nested models, you could compare them by chi-square tests. All the models are statistically significant when compared to the model that only used the pitching statistic and no fielding statistic. So that means that even errors is going to add some statistical significance in explaining the variation of runs allowed. Another thing we could look at is the mean absolute prediction errors, and we're going to get similar conclusions. So look at the chart on the left first. So the model using DRS here was off on average by about 22 runs. This was an average over the errors model, which was off on average by about 26 runs per season. Again, runs prevented and UZR performed similarly in the second tier, and FRAA and errors performed similarly in the third tier. Now, if you look at the chart on the right, these are the standard deviations of the prediction errors. So here, DRS at 17 had the lowest standard deviation. So that means that DRS was also the most consistent. This is all good news for DRS. It's the most accurate on the left, and it's the most consistent on the right. R squared is more your thing. Here's pseudo R squared values. Now we know that the best models are going to have the highest R squared values. Again, DRS is best with the highest values. The chart on the left shows marginal pseudo R squared values. So that means those numbers only consider the fixed effects. The chart on the right is conditional pseudo R squared values. These numbers consider both fixed and random effects. But again, it's the same thing. DRS is the best. UZR and RP are comparable as the second best, and FRAA and errors are comparable as the third best. Now, if you look at that model labeled none in white that I mentioned earlier, this is the model that only has the pitching variables in it, home runs, strikeouts, walks, and no fielding statistic. That has a conditional R squared value of 0.824. That means that 82.4% of the variance in runs allowed is due to pitching alone. So since defense is half in baseball, cut that in half, it becomes 41%, which isn't too far away from that 44% number that we saw on the first slide from the hidden game of baseball. Honestly, a more accurate title to this talk should have been measuring the 4 to 12.5%. At the lower bound, 4%, right? That's the number we get if we only consider unearned runs and errors. But there's more to fielding than not committing errors, right? Fielders' jobs are to get outs. So at the upper bound, 12.5%, this number comes from all of the opportunities that the fielders have to make outs. So to get the number, get rid of the run values of all the events that aren't balls in play. These are home runs and walks. So after you add up all the run values of all the home runs plus all the run values of all the walks, there's 37% run value left. So 37% of runs are due to not converting outs. Now, of all outs, 68% of those come from balls hit in play. These are outs that are not strikeouts. So 68% outs from balls in play times 37%, the run value available for the balls in play equals 25%. So I'd say at most 25% of defense is due to fielding. And remember, again, defense is half of baseball, so you get 12.5%. So I have a range of fielding equaling 4 to 12.5% of baseball. But even 4%, that adds up to 6.5 games. So this is a big advantage if we can get it right. We're not done yet. We still have coefficients to look at. Now, the red horizontal lines on these 3 charts, these are the true run expectancy values for each statistic. I calculated this by making the run expectancy tables over the same time frame and then calculating the run expectancy values for each of these statistics. And then the intervals are coefficients from the models that I converted to run values. So these are 95% confidence intervals. There are 2 things that jump out. First, all of the intervals encompass the red line, which is good. Second, the 95% confidence intervals, they're very wide. That's because I increased these by factors to account for multi-collinearity between the predictors. Okay, so these are the pitching intervals. Let's take a look at the fielding intervals. So here's the fielding statistic intervals. Here, the errors interval encompasses the run value due to errors on the left, which is good. Okay, but now let's look at the advanced fielding statistics. All of these should encompass -1 because each is designed to represent 1 run saved. That is not the case with DRS. 1 DRS only equals 0.28 to 0.87 runs saved. And that's even after I widened the interval to account for multi-collinearity. So that means that DRS is overvaluing fielding because 1 DRS isn't actually equal to 1 run saved. It's more accurately equal to 0.3 to 0.9 runs saved. But we can fix this. We can fix it by rescaling. So we can make DRS have a similar variance to the other fielding statistics. So if we multiply each DRS observation by 0.5762, okay, that's going to reduce the standard deviation of DRS from 44, which is the box plot on the far left, to 26, which is the DRS rescaled box plot. So that standard deviation of 26 is going to be more in line with the standard deviations of the other fielding statistics, which as you see range from 18 to 22. Now, when we rescale like this, the interval is going to become centered around 1, and we're going to keep the same model fit. So the model fit is going to be the same because correlation doesn't depend on scale, and model fit's based on correlation. So as you see in the table at the bottom, the deviance, error terms, and R-squared terms all stay the same between the DRS model and the DRS rescaled model, while the rescaled DRS more accurately represents fielding as 1 run saved. Okay, so these are my conclusions. I go back. So first, the DRS model is the best fit. UZR and RP, they're good alternatives. They fit better than errors, and there's no need to rescale UZR and RP. But DRS does overvalue fielding because 1 DRS is only equal to 0.3 to 0.9 runs saved. You can fix this by rescaling. When you rescale, it does not change the model fit. Okay, now the last bullet point, this is our big money question. Does this rescaling apply to individual players? Because if we reduce the DRS values for individual players, that would affect their WAR values, at least their WAR values that use DRS for fielding. So that's my recommendation for future research. So my research, I looked at the sum of the parts, the team fielding. The future research should look at the separate individual parts the individual player fielding. So that is all I have for this presentation. I hope you enjoyed it, and I am happy to take your questions now. Okay, so first, John asks, doesn't Savant's runs prevent it only focus on a fielder's range? Yeah, I do not know the answer to that question. Like I said, I didn't focus in detail on how each of the on the complex details behind the calculations. This is an interesting question. This is a question from Christian. Christian says, oops, lost it. It says, how would this change if you used XBHA instead of HR? Yeah, I do not know the answer to that question because I haven't tried any expected fielding statistics. I did try FIP instead of the 3, and I got similar results, but I tried to stay with what happened instead of what might be expected to happen. Another good question from Christian. It says, what if you included ground balls or even just weak ground balls? Yeah, I know in previous research when I've tried to do that, it sounds good in theory, but I didn't really get the results I was looking at. But your point is very well taken, and that's that pitching isn't just the home runs and walks and strikeouts. So to the extent that pitching is, getting weak contact, that'll cut down the amount of value that fielding has. Okay, so the next question is from Ben. Ben says, what about the R² model is pseudo compared to real? Good question, Ben. So an R² model is for a linear regression type model. That's when R² works because it satisfies all the assumptions. Once you get into the generalized linear model context, which I got into here by using a negative binomial, R² doesn't really work for that, but there are papers that'll do pseudo R² values that are similar. And I think I had that cited at the end of the slide. Jacob asks, have you looked into specific players at all? Makes me think of guys like Xander Bogaerts now and Derek Jeter late in his career not getting to the ball in the hole. Excellent question. That is my recommendation for future research, because my data set only include the team data. So it was the sum of the parts. I did not look at the individual parts, but we should definitely look at that next. So Christian asks, if DRS is the best, why rescale it to fit the other models? Well, it has the best fit, but it wasn't necessarily showing, it wasn't necessarily accurately representing 1 run saved as actually being worth 1 run saved. So you have to rescale it to make it say what it's supposed to say it's doing. I believe this is Dylan. See, it's cut off. It might be Dylan. It says, how long did it take you to do this project? Well, that's a good question. I'm very interested in this issue. So I've done sports analytics graduate classes, and I've always done some variation of this issue, maybe in like 3 different course projects. They were always, different and trying to answer the topics that we were studying in class. So I never did this type of presentation. So after 2 years of maybe doing those types of projects, I finally kind of put it all together how I would want to put it, not based on a class would want to be. So I've been doing it off and on for a while. So Mark says, really interesting presentation. Thanks. Thank you. In addition to a team variable, did you consider using ballpark as a feature? For example, are some parks easier or more difficult to field? Yeah. I don't think that would add more because I already use Teams. So I don't think that would be adding much more when I would be looking at it from a season level. In a variation of this project where I looked at this research on a game by game level, that's when using ballparks as a random effect showed was a lot more interesting. But when it's all averaged together like this in one big year, I didn't really get much from using ballpark, and I think I even did try it. So Stephen asked, have you looked at the relationship between these defensive statistics compared to war? Do they bear out the idea of a 4 to 12-ish% importance? Well, for the first question, no, I haven't looked at these defensive statistics compared to at least individual players' wars. I think I don't think there's a team war, right? So, and that's kind of where I really want to get to next. Because when you think about it, right, when you look at the overall sum of parts, it might be working, but the individual parts might not be working, right? Because stuff could average out to make it look like it's working. So this is definitely the next part for future research. Tom asked, do you have a full article style write-up for this talk? It's very dense statistically, sorry about that. And I think I would have to read it at a pace slower than a presentation to digest it all. I do not, but you could email me. My email address is my last name, schmerfeld@outlook.com, or you could find me on Twitter, and then I could get back to you and I could send you the paper, or you could contact SABR and they could give you the paper as well. Jensen says, what programming language did you use for this project? R, was all R. Dylan says, do you have an email you could be reached at yet? But really easy, my last name, schmerfeld@outlook.com. Feel free to email me anytime. The last question I have here is from John. Did you try breaking down runs saved for each metric by position group? I did not, but that's, I was thinking, I'm not sure how I would do that because I was using home runs, strikeouts, and walks. So I'm not sure how I would break those out by the position group, even if I could break out the fielding by position group. And it looks like I have one more here. Looking at the best and worst out rates on defense for individual players, the range is consistently about 10%. Half of that is 5%, which is in line with your numbers. Good. Thank you, Brian. I appreciate that. Anytime I get confirmation, that's helpful. So that is the last question that I have. Thank you again for being here. It's been a great presentation, and I'll turn it back over to Scott.
David, thank you so much for joining us. Always great to have some defense at the analytics conference. So appreciate you coming by.